Hello everyone. I'm Yash Kulthe, and I'm a PhD student at University of Surrey, and I'm here to present my work on watermarking of NeRF fields. S- So, yeah, just talking about the introduction, like why do we really need provenance? So, in today's world where like generative AI is becoming like more powerful and accessible to like everyone, and we have been seeing like a huge explosion of synthetic content, like everything from generated AI contents to like deep fakes and stuff. And well, like generally these models just allow us to like build anything from scratch just using a few prompts and all, like be it like images, videos, or even 3D assets and stuff. And like for example, like the images over here, you can see they have been altered, like the Pope in the court, and with like Rishi Sunak, the girl behind him has like weird eyes in one of the pictures. And like these images have been like edited, like possibly to like mislead or like fabricate events and stuff. So this problem is more of like a misinformation issues, where like to verify like from what source it came from or like what the content and stuff is like really important. But there's another dimension to provenance is about the ownership. So like suppose if someone creates maybe like a high quality image, video, or like a 3D model. So the questions that come is like who really owns it, and what if like someone just copies it and like maybe edits and like posts it on the internet claiming their own. uh, so yeah, I mean provenance is all about like answering those questions. It gives us the origin, the ownership, and the history of all of the edits or like the digital content. And like for provenance, we could just think of it as a digital label which tells us like who made it, how it was made, like or like has it been edited or not. uh, and well, one of the effective ways to like support provenance is watermarking. And like watermarking in really basic term is just having like a unique pattern on the visual content which can be used as an authenticator. For example, like watermarks on a currency notes and stuff. So the thing that we are working on is invisible watermarking, which is a process where we try to like hide watermark signal, like maybe it could be a name, an ID, or like a claim or anything. And this should be done like without affecting the visual quality. One of the examples that you can see over here, uh, where we take an image, a watermark, we try to embed it into the image, and then we try to extract the same watermark. And in normally in like 2D medias like images and videos, like watermarking is mainly used for like copyright protection, and this is done using like post hoc watermarking, which like we do it like which is like once we generate the content, after that we watermark the image or the video. But as generative AI has been like growing, it is like really hard, and I think it doesn't really make sense to like use the post hoc watermarking. So we need stuff where we are generating the watermarks while we generate that content from that model. And yeah, sorry, one more thing with this is the this triangle, which is like talking about the trade-offs of the watermarking. So one is in imperceptibility, payload, and robustness. We'll leave the security stuff for now. But so the trade-offs that we see over here is like maybe if we try to like increase the payload or the robustness, the quality would decrease. Or like maybe if we try to like increase the quality, like the other things would decrease. So it's all about like kind of like finding the right balance between these three. And well, so the motivation for this, so all of the stuff that I was talking about was about the 2D stuff, but like in my work, like I'm working on 3D. So just to explain like in short what is NeRF, I'm sure like most of you might be knowing it, but like just to like talk about it a bit. So NeRF is just like this one MLP where we what we try to do is like we have a set of images. Sorry, I can have this point, where we kind of like have set of these images, and we just try to like reconstruct the same image, and like there are many processes going through it, like resampling and volumetric rendering and stuff, but we don't really need to know about that. So the inputs is the position of the image and the waving direction and stuff, and we get the color and density as the outputs in NeRF. So why really watermarking is important in NeRFs? Because like maybe if for example, like maybe the use case of this would be like if I have like a 3D avatar of myself, and maybe if I'm using it like maybe in like a virtual simulation and stuff, and maybe like if people try to steal it, or like even the more simpler cases, like why wouldn't they like build the same NeRF field? Like maybe they could just take my images in the virtual simulation and like literally create the same NeRF the NeRF model from it. So we need a way to protect this. So that is why we really need NeRF watermarking. And well, there have been like many methods in the recent years that have been doing this, but mostly what they do is they just embed a single watermark uh, into the model, as you can see over here. And also the major limitation with that is that the maximum bit payload capacity that they have achieved is like around 48 bits, which is like not really realistic when you try to like see it, like if you were trying to like embed some information into it. And the second thing is and the second thing is to like try to embed multiple watermarks. So the use case of this would be like maybe in commercial settings where like maybe like large projects are being handled by like multiple people. So we might need like multiple watermarks to like show the ownerships for like those multiple people. And the third thing is to like condition those watermarks according to the user inputs and stuff. uh, yeah. And well, these are set of challenges, or what I call a set of rules for NeRF watermarking. So the first thing is like as NeRF is like a continuous view dependent representation of a 3D scene. So we really need like watermarks persistent around like all of the viewpoints, not just like specific training viewpoints. And the second thing is like we can't really use post hoc watermarking. We need like generation time watermarking over here. So yeah, finally talking about my main work. So it is about like embedding of multiple watermarks into NeRF. Uh, and well, as I told, that existing watermarks only like embed up to like 48 bits, making them insufficient. So multi-NeRF addresses this issue by embedding multiple watermarks into NeRF. So for example, if we have like 16 different watermarks of 16 bits, which would be like 16 cross 16, that is like we are embedding like 256 bit watermark as a overall in this scenario. And we do this by conditioning each of the the watermarks according to the user inputs. Like over here, like we have like sets of user inputs like I, A, B, or C, and we have like different watermarks for them, and we try to like reconstruct the images and like embed those same watermarks for that specific user IDs. um, and well, the NeRF architecture that we use over here is TensorF, and we kind of like have a bit of like extensions that we add to it. The one thing is the watermark grid, the second thing is a film based watermark modulation, and the third thing is like differentiable augmentation to like increase the robustness during training. So yeah, to avoid interfering with the appearance or geometry, as I told, that NeRF outputs the color and the density fields. So a basic architecture of TensorF would be like the bottom two grids. So these are the grids that I'm talking about, and uh, the first grid would output us the RGB values and the density values in normal TensorF, and in our case we have added a separate watermark grid, because like in previous works, like what they have been doing is like either they try to embed the watermark into the the color field or the density fields. But for us, we like added a new watermark grid, which is like similar to the others, which outputs as these watermark feature values, or like yeah, like a feature field or something. And with this we try to like modulate it. So the how the modulation works is that we would have like unique user inputs, like discrete integer values, and we would like just have like a embedding layer for it, and then we would feed it to the modulator. So the modulator is just like a linear layer which outputs like two values, which is this gamma and beta. So the gamma acts as a scaling term for the watermark features, and the beta acts as the shifting terms. So this literally is kind of like acts as a switch to like switch between like the different watermark ID, different watermarks according to the input IDs. Um, yeah, so that is the architecture. And while talking about the training process, so I've just divided into like two phases, but this is like a whole end-to-end process. But just to like clearly understand, I've like divided into two phases. So one more thing over here is that we are using a pre-trained decoder called Hidden. I'm not sure if I cited it anywhere. Oh yeah, I've cited it over here. So we're using a pre-trained decoder called Hidden, and in the first phase, what we do is like we freeze the hidden decoder, and we train the nerf or the like the embedding in the modulation layers, and then we try to like decode the watermarks using this decoder. And before that, like when we render out the image, we also have like a level 2 decomposition of discrete wavelet transform, and we take the lower frequency, that is the LL sub band of the rendered image, and then we feed it to the decoder and try to like decode the message. And this is purely to like increase the robustness, because like people have been doing this in like previous works, and it like increases the robustness against like compression attacks and stuff. uh, and also to like ensure like robustness, we also apply these differentiable augmentations during training, which consists of like stuff like JPEG compression, blurring, contrast, and like normal transformation attacks like those. And the loss functions that we use in phase one are the bit accuracy loss, which is the binary cross entropy, and the perceptual loss. And then in the phase two, we switch to a patch based approach, where we kind of like take a patch, and we do this purely because like it is just memory efficient, as well as like we kind of like get to like control the local image quality. And the losses that we use over here is the normal RGB reconstruction loss that is used for nerves, the SSIM, and the total variation loss to like reduce the high frequency noise and stuff. And also one more thing, while we're using the differential augmentations, we also need to unfreeze the decoder so that it learns to like adapt to like those attacks or the augmentations. So yeah, these are the results to evaluate like multi-nerf. As there were like no multiple watermarking algorithms. Uh, Sorry, as there were no multiple watermarking algorithms left. Sorry, not left, but there were no multiple algorithm baselines, so we had to like compare it against single watermarking. So as you can see that it performs better than the others. And for the multiple watermarking case, we didn't really had any baseline. So what we did was took one of the single watermarking case and like tried to like embed multiple watermarks into it, and you can see over here that we get like a boost of like 20% bit accuracy for like both of the data sets. And like talking about the robustness, well, we tried like these different tags and stuff. And well, this is the model with the augmentations. And the one more thing to note over here is like we also tried like the watermark removal attacks, and like our method did really good than the other two. So we tried like diffusion and like variational autoencoder removal attacks for this. And I don't really think that I have time to go into ablations, but just one thing over here, like we did like a user study over here where we like kind of ask the user to mark the artifact score. More is like we have more artifacts, and less is like we don't really have any artifacts. So well, I mean, like with this, like you can see that we have the least artifact score. So with this, like we can prove that like we do not really kind of like lose the image quality nor the robustness. In fact, like we are better in the robustness, but we also did increase the bit payload capacity. So just coming back to like that triangle thing where like we had to like adapt to like something, and like if we increase something, like other would decrease. But over here, like not the image quality is gone down, not the robustness is gone down, but like we increase the bit payload capacity. Well, yeah, these are the results. Ground truth image, watermarked image, and these are the residuals, like just to see like where the watermark has been embedded and stuff. And one more thing with the results is that the left image is the single watermarking algorithm where we try to embed the multiple watermarks, and this is our method. Well, you can see like if you really try to like uh, put like more bit capacity, like you would decrease on the quality. So as you can see, like it has lost the reflections and stuff, and also like you can see these artifacts, the watermarking artifacts, but you don't really see that in our method. And yeah, I mean, just to summary, like I'll just go through it quickly. Yeah, we did like multiple watermarking using the grid and the film based modulation, and like the conditional module acts as a like as a switch between to like switch between the watermarks according to the user inputs. We did increase the capacity, and well, the multi-nerf noise is like more robust than the other methods against like the watermark removal attacks and stuff. So yeah, thank you. I've just added a QR for my poster because couldn't really bring my poster today. So if anyone's interested, they could just scan it. Yeah, that's it. Thank you.